So what is the purpose of artificial intelligence? Well, it can be summed up in one sentence, which is the purpose is to teach a system how to not only perform a task or series of tasks, but to also create effective new solutions for circumstances for which it was not trained. So what we're talking about is task following versus adaptive response. So with programmed robotics, they cannot think outside the box. Here you have a bunch of automobile assembly line robotics carefully doing welding and assembling pieces onto the cars, and they do it very efficiently. But if you were to make any changes without reprogramming them, they wouldn't be able to take on the new task. So everything's very structured, and they have to follow a procedure. Whereas with artificial intelligence, we're talking about intelligent robotics, intelligent systems that can think far outside the box. In other words, they're trained, but then they can use what they've learned and go outside, extrapolate to come up with new solutions. So now we're going to talk about a specific application, which is applying neural networks to a unmanned helicopter, small unmanned helicopter. And this is a control block diagram just showing you where the neural network fits into the picture. This is a sort of a sub-module, which is the pitch control module, and simplistically set up, but this is the way it works. You have the aircraft or the helicopter. The aircraft is maneuvered through the control surfaces, which are the rotor disc and the tail rotor. And the way those control surfaces are given commands is through the aircraft servo actuator servos. Then when the aircraft moves, there's sensors such as GPS and the inertial sensors to let the control system know what's happening. So in this particular case, the aircraft is pitching, then this will be picked up by the inertial sensor, and this passes the pitch attitude error and pitch attitude rate to the pitch neural controller. The neural controller that then provides a compensation response is trying to correct the movement of the helicopter. So we call this the pitch controller servo signal. This comes back and goes to the pitch servo actuator, which would control the pitch control surface of the main rotor. And then this is just a continuous loop. So every time there's any kind of pitch attitude error, or the pitch commanded pitch is different and there's some error off of that, then this is fed into the pitch neural controller, and then it provides a feedback signal to try to correct the aircraft's attitude. And then this applies to the roll as well, and any other parts of the system, such as velocity control along the x-axis, y-axis, and so on. The next thing is training of the neural network control system. The training objective is pretty basic. It's just to stabilize the helicopter and hover with no winds. That is, if we successfully create a neural control system, that's all that we want it to do. The training conditions for attitude control were the following. The helicopter was mounted on a test stand, and we commanded a decreasing sinusoidal wave input to the rotor disc and recorded the attitude response. That's how we obtained the transfer function or dynamic response of the system. This was the data that was actually used to build the neural attitude controller. So the following is an example of how the helicopter was modulated on the test stand. This is a crude animation, but it just shows a decreasing sinusoidal wave. So the rotor disc was commanded, and then the attitude data was recorded, and this was used to build the attitude control system. The training conditions for velocity control were the following. We had a pilot that flew a simple forward flight maneuver and then stopped the helicopter, and that data was the basis for the transfer function or dynamic response of the system, and that's what was used to create the outer loop neural network controllers. In the following video compilation, we're going to go over the test results. Note that the system achieved additional objectives for which it was not trained. So the neural network flight controller stabilized the aircraft with a sling load. This is very difficult even for a skilled pilot. So not only did it hover the helicopter, but it stabilized it with a sling load. It was able to fly forward, backwards, sideways, ascended, descended, took off, and landed, stabilized the aircraft in gusting winds, and was able to stabilize different aircraft sizes and power plant types, such as gas, electric, and two-stage turbine. And we'll see this in the videos. Here the helicopter is carrying a sling load. As you can see, it's very stable. And this is an example of the neural network flight control system going far beyond what it was trained on. This is a continuation of before. In this case, the helicopter is carrying the sling load in forward flight. As you can see, the sling load is very stable, so the neural flight control system is going far beyond what it was trained on. In this case, what you're going to see is the helicopter waiting while the little robot gets on board the basket, and then it'll pick it up and carry it a little ways and then deploy it back to the ground and let the ground robot leave it. But this is just more of a demonstration of how well it carries a sling load and for different maneuvers. And again, it goes back to how well the neural network goes beyond what it was trained on. This is the neural flight control system handling electric helicopters. There's two of them just hovering. But again, it's just another example of how the neural control system can handle different power plants, electric, gas, etc. This is an example of the neural control system not only handling a different power plant, which is electric, but also very gusting winds, very much with ease. This is a different gas power plant, smaller airframe, but no problem for the neural control system, both hovering and also landing the system. This just shows how stable the system is from the helicopter's perspective. This is an example of the neural control system handling a different power plant, which is a two-stage turbine helicopter with a very large rotor span, 8 feet. The typical one was more like 5 or 6 feet. And again, no problems handling takeoff, hover, forward flight, etc.